So hello everyone. Welcome back to CS11-737. This time I'm very happy to have Orhan Firat, a research scientist at Google Research, talking about universal translation at scale for our guest lecture. Orhan, I think if you're in the field of multilingual processing or anything related to it, you will know of his work. And notably, he did some of the first work on multilingual translation using shared attention mechanisms between many languages way back in like 2015 or 2016 or something like this. And ever since then, he's been innovating in the space of multilingual translation. And he got his PhD at Middle East Technical University and was a visiting researcher at University of Montreal and working together with Kyung-Hyun Cho from the early days of neural MT. So he has a lot of stuff to talk about, so I guess I'll let him speak for himself here. But thanks a lot for visiting, and we're really looking forward to it.
Thanks a lot, Graham, for the generous introduction, and thanks a lot for inviting me in the first place. I'm very excited to be here remotely. And hi, everyone. Thanks a lot for your interest. I'm very excited to talk about the stuff that we've been doing for over 2 years at Google that is spanning multiple teams, like over 30 people. And you'll notice the problem is, although it says it's multilingual machine translation, you'll see the problem is sometimes a systems problem. Sometimes it becomes a core machine learning problem, or sometimes it's basically a data preprocessing or data related issue. So I'm very excited to be giving the talk, and also very excited to and feel really privileged to be part of this great team at Google. So the title is Massively Multilingual, Massive Machine Translation, but at the end that's what our goal is, basically trying to come up with a universal translation model, and the implication is basically we have to make it at scale. I want to apologize beforehand. I'm feeling a little bit under the weather, so my voice may feel a little bit not loud. Apologies beforehand. And please, at any point, if you have any questions, feel free to ask questions. All right. So as I mentioned, our goal is to develop a universal translation model, or universal machine translation model. But the universality is a vague concept. If you say, okay, I want to build a universal machine translation model, it may sound a bit romantic. So we actually had to formalize this goal first in the first place. So in our formulation, what do we mean by a universal translation model? It has to cover as many languages as possible. That's the first requirement. And the second one is, as we get more and more languages, this model or this engine should be able to adapt to new language or acquire this new language with minimal sample efficiency, with maximal sample efficiency. So that's what we mean by universal machine translation. So it's, as I said, it's a little bit of romantic goal, but actually there is a research question behind this great endeavor. So what we're trying to do at the end of the day, we are asking the question: can we parameterize and learn a communication medium that is diverse across all these languages? This was coined as interlingua, and our way of attack is going to be using connections paradigm, meaning neural networks. So at the end, the question is, can we actually learn interlingua using connections paradigm or neural networks? So it might have it might feel a little bit, yeah, you can right now, but it was not being the case for the last 50 years. We are still not very confident whether we can do it or not, but that's the research question that we're trying to answer. And the whole slide deck that we have here, or whole the project, is basically trying to answer that research question. And as a spoiler, even if I wanted to write down everything in this slide deck into a paper, I wouldn't be confident to say yes. So this has been really a long marathon for many of us. Okay, but what is our motivation concretely to be able to build this universal translation model? The first goal is if there's going to be a single model that is translating across all the languages, so it has to improve the translation quality across the board for all languages. So what do we mean for all languages? So we can actually build a system that is mediocre for several languages, but so that means that wouldn't really satisfy the need for universality in translation. So what do we mean by improving quality for all? So in order to understand the question, we first need to look at the data that's our hand, because at the end we are building a machine learning model that relies on data. So here we plotted the data distribution over language pairs. So I'll be using this plot a lot throughout the talk. So I'll be spending a few minutes on this. So here, this is the data distribution over all language pairs that was in our initial study. And on the x-axis here, you can see 103 languages sorted from left to right with respect to the amount of available training data. So it means what we use as training data, we use parallel sentences. And here we basically plot the distribution of all these training data, which adds up to 25 billion training examples. But since in the x-axis we have 103 language pairs, on the left-hand side you see high-resource languages, which we have a lot of data, sometimes even surpassing billions of examples. And for those languages, the translation quality is really good. It's almost reaching to human quality for some certain domains or for some certain scenarios. But as you go towards right, you're going to see low-resource languages. There we have very limited amount of data, almost 2 orders of magnitude less data compared to high resource languages. And for those languages, the quality is actually not that good. So low resource machine translation or low resource NLP is trying to actually improve the quality of the right-hand side of this distribution. So our goal is basically improving the quality both for the left-hand side and for the right-hand side. So the second motivation is expanding the language coverage. If you remember the previous plot, so I mentioned the x-axis has only 100 languages, but that's not all the languages that is out there. So there are actually around 7,000 languages in the world, which Google Translate covers only 112. There are 2,000 or more than 2,000 African languages where Google Translate only covers 12, and like out of 700 Native American languages, unfortunately, Google Translate does not support any. So the goal here is also expand the language coverage, or if you remember the previous plot, basically extend the x-axis to its extreme. So how are we going to do it? So increasing the quality across the board. Like any other machine learning model, our approach is also using some inductive biases. So increasing the quality across the board, we're using basically 2 inductive biases. The first one is the positive language transfer. Here, the inductive bias of multilingual machine translation is the learning signal from one language should help to the learning of the other language that is resource poor. So this is the positive language transfer inductive bias that we're using, and that's what we're going to leverage to improve mid to low resource languages. But the other inductive bias or the other empirical evidence that we have is the scaling of neural networks, or the scaling being observed to improve the generalization of neural networks. So that is what we're going to use to improve the quality of high resource languages. But of course, to be able to do that, we first need to build systems, which is usually overlooked, but I'm going to go into the details of that too. The second one is expanding the language coverage. So I talked about high resource and low resource languages, but like how are we going to expand the language coverage? That's a completely different story. So, and if you start to extend the coverage beyond 100 or 150 languages, you'll notice you won't be having any parallel data, which does not really fall into anywhere in the plot, in the data distribution plot that I had. So there we're going to be using techniques that ingest monolingual data plus parallel data simultaneously. And so if you're familiar with the current landscape of the field, monolingual data is mostly being used by unsupervised machine translation techniques, and parallel data is being used by supervised multilingual techniques. So here we're going to be trying to confluence these two lines of research. But of course, we also talk about how are we going to find the monolingual data in the first place. And also the last one, how are we doing this? We talked about the models, we talked about the data, but machine learning also requires us to fit the model on the data at hand. So there is also a learning or optimization part of the problem, which is quite important, as important as the others. There we will be tackling with the challenges like balancing the transfer or interference or positive or negative transfer between languages, and we're going to be seeking suitable architectures for that. And also how we can actually manipulate the learning signal explicitly to aid or ease the learning of another language or another task. There we're going to talk about what bottlenecks that we have and what observations that we have at our hand. So like after these two slides, so it's quite obvious. I think this is a really compelling test bed for machine learning research. Massive multilinguality requires us to advance basically approaches on multitask learning, meta learning, or continual learning, and also massive scale requires us to study how to define model capacity, how to tackle with trainability, optimization challenges to generalize, to make these models generalize. Also, after building giant models, how are we going to make them efficient? Okay, I'm going to be giving the final 3 slides or the summary of the whole entire talk in this next 3 slides. The first observation is multilinguality improves low resource languages. It also improves higher, like I should have said like mid to low resource languages. Here, what we are seeing in this plot is in the x-axis, we collapse all the bilingual baselines into 0 score or 0 baseline. And then we plotted the trend line of a single massively multilingual model using this like blue curve. So there you can see on the left-hand side, high resource languages, they're actually regressing a little bit compared to their baselines. Remember that we were using a lot of supervised data for those languages. But on the right-hand side, we're seeing a lot of positive language transfer. Measured in terms of blue, it's sometimes like more than 10 blue score for some languages. So that's the first take of the entire project. The second take is about the second massiveness in the title. As we scale these models more and more, scaling improves overall translation quality. That is across the board. So just to remind, we use multilinguality to boost the quality of low resource languages. And we use massive neural networks or scaling neural networks in order to boost quality for high resource languages as well. But the third bullet or third takeaway from this talk or from the project is we also have found techniques or studied techniques that allows us to make use of monolingual data plus bilingual data simultaneously in order to extend to new languages. So that means as we go beyond 100 languages, here I plotted the original data distribution on the left, you're seeing in the light blue, and I overlaid the available monolingual data for up to 400 languages. So as you can see, we have a lot of monolingual data beyond 100 languages, but the bilingual data or supervised data, the amount actually drops quite quickly. So we're gonna, if you want to extend beyond 100, so then you have to delve deep into unsupervised MT territory. There we're going to be using self-supervised learning and how to basically how to come up with a symbiosis between supervised learning that is leveraging the blue data here and using self-supervised learning or other techniques that we incorporate to make use of the gray area, which is monolingual data. So these 3 are basically the main takeaways of the entire project. Are there any questions so far? Okay, I'll move on. So there will be 5 sections in the talk, where the sections basically follow the separation or clustering of or separation of or dissection of this formulation. So here we have a function f, We have x as the data, theta as our model, and mu as our hyperparameters or the techniques that we use to optimize our model. And it returns us a quality that we try to improve. So we're going to be going on each of these variables. So the first one is data. We're going to be talking about the sentence level machine translation, but they're actually arbitrary length. Second, we're going to be talking about the model, theta here, architectures that are enabling or enabling us to train these giant models. There we're going to be talking about how we wire or how we learn to wire these models and how we parameterize them, how we stack up layers and so on. And in the third one here is the training or fitting. So there we'll talk about the loss functions, how do we optimize, or other techniques that we basically learn given the data and given a model. But there are actually two more crucial components that are usually overlooked, which I will try to cover in this talk. So the fourth one is the systems part of the entire problem. I talked a lot about the scaling component, but scaling requires stable and robust systems, which we usually overlook. So here I also talk about systems because at the end, systems are what help us orchestrate all these variables running or interacting smoothly. So what do we do using systems? We train our models using basically manipulating this distributed infrastructure. So there I'll talk a little bit about model and data parallelism frameworks that we have and how they enable us to train giant models. Basically how systems enable us to answer the research question that I mentioned at the beginning of the talk. And the fifth one is the downstream transfer or the quality. I mentioned the quality measured for machine translation, but it's not the only thing that we are looking at right now, these days at least. Because if you're training a giant model, so you're not going to be training hundreds of those giant models. So if you have one giant model, then the question is it also useful for other downstream tasks, especially cross-lingual downstream tasks? So we're going to talk a little bit about what's in it for me if I have access to this giant model and I'm interested in solving other tasks, the task other than MT. But there we're going to be talking a little bit about salvaging pre-trained machine translation models. So this is basically the overview that I have. So let's dive in. The first one is about the shades of the training data. So I'll talk about the progression of the project. Here, I put the distribution of the data that's at our hand, and we trained first bilingual baseline models that have the same capacity with a single massively multilingual model. So here we are basically fixing the capacity and training a single massively multilingual model for all these languages, and then comparing them against each one of these bars that you see that correspond to a single bilingual baseline. So here, for example, on the left, you're seeing a transformer big trained for English-French machine translations, and its quality is reaching somewhere around 40. And towards the right, a single translation model is trained for example, Hawaiian, and the translation quality is actually not that good. Now we're going to collapse this blue scores into the zero baseline and then use them as our bilingual baseline. And we're always going to compare our multilingual models, either the multilingual models by using that baseline. And we are going to be aiming something that looks like this without scaling. So if I'm just making my models massively multilingual, so I was expecting the quality to improve on the low resource languages, which is on the right-hand side. And this is the ideal plot that we aim at. But let's see, are we really getting that if we train a single massively multilingual model with the same number of parameters compared to bilingual baselines? So unfortunately not, but let's dissect these two plots. So first thing, our data is English-centric, which I didn't mention before. So that means our data set consists of examples from English to other languages or other languages into English. So if you train a multilingual model using this data, you end up with basically two directions. The first one is one-to-many, which corresponds to English to any other language. And within the same model, you also train many-to-one pairs that correspond to any other language to English. So this is how we're going to be reporting the results. So that's why I'm explaining this plot a little bit in detail. Here on the left-hand side, the left panel corresponds to English to any translation performance with multilingual baselines. And here in this case, let's just focus on the green curve. I'll be talking about the blue one later on, but let's just focus on the green one. Here on the left, when we're going out of English, we're seeing quite some regression on high resource languages. But as we go towards right, at least we're getting above the bilingual baseline, bilingual baselines. But the transfer is not really apparent. But let's look at English to any scenario. Here, let's again just focus on the green curve. Here we have on the high resource languages, again, we're regressing. But that was, again, not our goal because we have the same capacity with bilingual baselines, so it's kind of expected to regress or to not as good as the bilingual baselines. But as we go towards right, we're actually doing quite good in terms of the low resource quality. So this is basically what you're going to get if you train an equal capacity model, equal capacity multilingual model compared to your baselines, and by doing very simple tricks like oversampling. But this relies only English-centric data. That's why we have left panel and right panel split. But actually, the world is not always looking, or this is basically an artificial scenario that we induced. Since the internet is dominated by English, we were able to find a lot of English to X data or X to English data, which is what I mentioned by English-centric. That corresponds to the figure on the left. But if our goal is universality, so we should be able to translate between any two language pairs. So and you end up with a graph that looks like the one on the right, and that's what we call either complete or fully connected graph or fully connected bipartite graph. So, but the question here, okay, where am I going to find this data then? It's quite actually, what we did was quite simple. We actually looked at the available English-centric data that is on the left, and we looked at the overlapping examples between, for example, in this case, Spanish English and German English, and we simply looked at the English side overlap. Okay, are there overlapping examples on the English side? And if there are overlapping examples, and then we basically separated those examples as three-way aligned examples. So then what we end up with was a multi-way aligned data between Spanish, German, and English in this case. So we actually repeated this process at scale, and that's what we found here. Again, I overlaid the average translation per example on the amount of data, or on the training the data distribution that we had previously. So here the overlap is pretty high considering the amount of parallel data. So here on the red, what we're seeing is, for example, for one language, for this low resource languages, for one example, we were able to, in average, we were able to find 12-way parallel examples. So basically, that Swahili example had, in average, 12 it was aligned with 12 other languages. So we basically exploited this fact or exploited the structure in the data, and this allowed us to extract 70 billion additional examples. So we actually have a WMT paper which is going to be presenting, I think, the other day, or in 2 days. There we also repeated this experiment on WMT, and the results are quite similar to this one that you see here, but at a lower scale. So then, after having this data, we again split the entire, we train another massively multilingual model using the concatenation of the 70 billion examples plus 25 billion examples that we already had. we basically put all this giant data set, and then we trained a single massively multilingual model on this data set. So here we end up with like almost like, a model that can translate between 12,000 language pairs, sorry. That is again for 100 languages, 112 languages. But if you edit, like if you count all possible pairs, you end up with this number. So this is a model that is truly complete, and it's not basically using any additional data in terms of monolingual data, or it's not crawling any additional data. It's just exploiting the structure in the data. And the results were quite surprising, or not surprising, because we were in the regime of supervised training of all the pairs that we were previously not training. So there we observed on from English to X, or one to many. This was actually boosting the quality quite a bit. And when we were going into English, we were seeing some degradation in the performance, because if you think about the decoder or the examples that the decoder language that the decoder is seeing, this time it wasn't dominated by English. It was like basically a more balanced recipe across all languages. So we were seeing some degradation. But on the rightmost column, you see the quality boost compared to bridging baselines that we had. And sorry, this is compared to zero-shot baselines that we had. And the quality gain was huge here, and that is in average. So we average, for example, 30 languages, and that add up to 11 blue score for mid-resource languages. But this is just for, so these two examples, we're using bilingual data only, and how we can, like we were trying to answer how we can exploit the structure that already exists in the data. Of course, there are so many other ways to, or so many other ways of like structure that we can exploit in this data set. But that's where I'm going to end this part, because the next part I think is more exciting. That is about going beyond 100 languages. So if we want to go beyond 100 languages, so we are basically in the territory of unsupervised MT. So what we have seen so far was multilingual models were bringing quite a lot of improvements on low resource languages, and they were quite close to what we were calling, if you combine them with complete models, so they were actually close to interlingua. Of course, it requires further investigation. But simultaneously, there's been a lot of progress in unsupervised MT, but it has some deficiencies if you consider using only unsupervised data. So just to name a few, for example, unsupervised MT does not seem to be working quite well when the domains are not matching, or the languages that you consider are not linguistically similar, or they're quite distant. So what we were proposing, if you train a massively multilingual model, what you end up with is a huge coverage in terms of domains, in terms of scripts, and in terms of quite a lot of things that unsupervised MT was suffering. So there, like our approach is basically jump-starting unsupervised MT using massively multilingual models. So how? So we have to teach massively multilingual models to make use of monolingual data first, and address the deficiencies of unsupervised MT. And as we go beyond 150, actually, there we noticed that there were not even language identification models that we can get monolingual data, even monolingual data. And then, like, we actually worked a little bit on new language identification models, or how we can get this data for more languages beyond 100. And at last, we demonstrate like how all these three steps combined works at scale. So let's look at monolingual data first. This is the parallel data in WMT, and what we have, if you also overlay monolingual data, we always think, oh, okay, monolingual data is quite a lot for all these languages. But the story is a little bit different in the real world. So if you look at here, yeah, the story, it's actually following WMT up until, say, here, if you look at the middle, that corresponds to almost 1 million examples. So think like you only have 1 million example sentences for a language pair, and you resort to unsupervised MT techniques that are already quite brittle. So it's actually quite challenging to learn these new languages. And you also and the things are actually getting even worse and worse as you move to the right. So what we do is basically come up with a symbiosis between supervised and unsupervised MT. So what we are doing, what we were doing is basically leveraging monolingual data with self-supervision, while we were ingesting bilingual data using supervised learning. So on the top that you're seeing our classical approach that use only supervised data, and at the bottom you see while you're training, you're ingesting both monolingual data using supervised loss that you already have. Sorry, using monolingual data with self-supervision and use parallel data using supervision that we were already doing. So what particular loss function that we were using? We were making use of this MES that was proposed by Microsoft last year, and we found it quite efficient and effective to make use of monolingual data to pre-train sequence-to-sequence models. So from here on, whenever I say self-supervision, that will mean that we're going to be using MES as our loss function. And so we we did some experiments. Okay, can we just, what happens if we follow the recipe, the second recipe that I showed in the previous slide? Here we're showing some experiments on WMT. The details are here at the bottom of the page. I attached a link to the paper. So here in blue, you're seeing a multilingual model that is trained without using any monolingual data, when by using only supervised loss function. And in red, that you're seeing the recipe that I showed in the previous slide. So that interestingly, even for high resource languages, the use of self-supervision plus supervision was improving the quality. So that may actually have something to do with the prevention of domain shift when we use monolingual data, which I'll talk about at the end, but I just wanted to mention here. But this was not the only benefit. Here we only tested, okay, let's just use supervised data plus monolingual data, sorry, parallel data plus monolingual data, and train the model without doing any back translation. Okay, it's doing good. But now what we tried, we actually separated one language. So here, and we separated one language and then simulated the scenario of a new unseen language that comes with only monolingual data. Here on the left, let's focus on the center panel here. Here we are doing Latvian to English translation, and the left column is basically a multilingual model that includes Latvian data already. And on the right, that we trained a multilingual model without any Latvian data, and mastered this new language by using only monolingual data. And compared to the supervised baseline, we were actually getting quite close to the oracle that we could have gotten. So that was quite encouraging. And another benefit that we noticed was as we incorporate self-supervised losses, we were also noticing an improvement in the zero-shot translation. So somehow the representations that are learned by these models were getting either better in terms of their smoothness, or they were being more plausible for zero-shot machine translation. Here you're again seeing the zero-shot quality of all the models that I've shown in the previous slide. On the left, we have multilingual model. In blue, we have multilingual model that's not using any monolingual data and self-supervised loss function. And in red, you're seeing the model that is ingesting both types of data. And we replicate it in multiple scenarios, either with 15 languages, 3 languages. It was pretty much the same result. But we didn't address any of the inefficiencies of unsupervised MT, right? So I said like unsupervised MT has some deficiencies, but we didn't address them so far. So then what we need to do, we need to show how we can harness multilinguality more and more, because all the previous experiments were in the setup 1, which was only using self-supervised learning and supervised learning. But these are not the only objectives that we can actually make use of. We also have back translation objective, which can augment more and more data, basically spit up some pseudo parallel data given any monolingual set. We also came up with this cross-translation term in order to use indirect supervision for a new language. Here, I zoomed in the cross-translation objective. Here we have monolingual data only for Romanian, but we have indirect parallel data between English and French. So here what we were doing is we were making use of Romanian monolingual data to, for instance, translate a backward translation model here, while we were also translating a French sentence into Romanian first, and then that Romanian pseudo translation was translated into English. And then we were actually using the fact that English and French has parallel sentences, and we were actually doing the same thing in the other direction. And then we were updating these models all together. So here the cross-translation term leverages the indirect supervision between English and French to improve the quality of this new unseen language, that is Romanian in this case. And of course, in all these unseen language cases, we're not going to be touching anything in the vocabulary. So we're assuming the vocabulary already covers that new language. So that's another problem that I'll be talking towards the end. But making use of this last setup here, we studied in a more say challenging scenario where we have very rare languages that have, for example, Nepali, Sinhala, and also the data that we incorporated for some of these languages, for Kazakh and Gujarati, they were actually coming from another domain. So they were actually quite out of domain. So this is the scenario that we tested, whether this massive multilinguality can mitigate the issues of domain mismatch or not met the linguistic the distance in terms of the linguistic similarity. So here are some results that we have by using the previous objective or previous setup that I showed. So the take here, like I know this is like a huge table, but let's just focus on the middle section here. So we have a three-stage approach. We were like as I showed here in the previous slide, the first panel is the first stage, the second panel, the second block is the second phase, and the third block. So what the difference here, or what we do in these stages, we incorporate a new loss function. We do more online back translation and so on and so forth. But while you turn on the gears of massive multilinguality, so it also opens the door for you to use so many languages that you can actually manipulate indirect supervision, and so much monolingual data that you can translate between any other language and then boost the quality of the overall system. Here, what we were showing is basically at the end of stage 3, we were getting quite competitive results, both compared to previous unsupervised NLP approaches, and they were even sometimes competitive with supervised approaches that were submitted to WNP last year. So far I talked about how to make use of monolingual data and parallel data. Now up until now we assume that these data is already available to us. Now I'll be talking about what if I want to go beyond this 400 bar, or what if I want to go beyond the chart here, like 400 languages, and the challenges there.
Hi, yep. Orhan. I had 2 questions, and maybe other people might have questions as well. So my first question was, I found the graph interesting where you incorporated monolingual data and you saw larger gains for into English instead of out of English. I was wondering if you had any ideas about this. Like, I would have expected essentially like the gains on out of English to be larger because you're better training the language model with lots of monolingual data on the target language. Do you have any insights there?
I see. You mean this plot?
Yeah, that
Is
one.
this?
Yeah.
Okay. And the question is, we are seeing more gains into English. Is
Right.
that? So this is the first phase. That's a good question. This is the first phase, and the models that we have are already good in translating into English. So they're already good, and that's the observation is without using any back translation, they're only good for into English. And if you want to boost the quality, you have to augment that. You have to stop at this point and then generate more and more data to boost the quality of the right-hand side here. So that's what we used in the other stages. But I don't have a concrete answer. But my I think that the one possible reason being the overall quality being low in this direction into out of English. That's my guess, but we haven't actually controlled. Like we don't really have a concrete answer to the question.
Okay. And then my second question, this might be a little bit of a silly question, but for the Lithuanian results, so sorry, Latvian results here. So I was wondering, did you try training it without any monolingual data whatsoever, or applying the model without any monolingual data whatsoever to see how well it translated without any sort of unsupervised training? And the reason I ask is because Latvian and Lithuanian are very, very similar. So like in our previous results, we applied a model that had another very similar language without even training it on that language at all. And I was just wondering, like, how much you were gaining over, that really simple baseline by adding monolingual.
I see. So I think the answer here is on the right-hand side in Hindi to English. So as we see, if there is no relevant languages in the mix, which is on the left-hand side, you're not actually getting that much gain, but it's still like, say, about 10. So left-hand side, like Lithuanian and Latvian, if they're close, so they're actually benefiting from each other, probably boosting the quality of each other. But there's no other language that Hindi can probably make use of. So yes, but that is also the assumption of like massive multilinguality. As you increase more the language coverage, you're also increasing the chance that you're going to be finding a similar language. So yeah,
right.
Does that answer your question?
Yeah, more or less. I think it still might be interesting to see like what would happen if you had the multilingual without Latvian data with no monolingual Latvian data, just to see how much you were gaining from the self-supervision versus how much you already had without doing any self-supervision.
I see.
But that's obviously you probably don't have the experiments. So
yeah. No.
Cool. Are there any other questions that people wanted to ask? We can do chat, or you can just ask orally. Okay. If not, we can continue on.
Okay. So surprisingly, this section is not going to be technical. So because we're going to be talking about the first observations as we try to extend this x-axis beyond 150. So interestingly, the current approaches to like finding data or mining data rely on language identification models that are either off the shelf or that are out there already for 150 languages. And it's like felt like while they were doing this research, this paper that is at the bottom, it felt like the academia was treating this problem was almost solved. So we did a deep crawl of the web for almost 400 billion web pages using so we actually curated some a data set and then trained our language identification models on this mixed bag of everything, basically. And then we did a very deep crawl. And the resulting data was extremely noisy. So it wasn't actually that good beyond 150 languages. So here we put some examples, but the ones that I was remembering. So we found we found so many examples. For example, a language written in the script of another language, which was basically breaking all our language identification models, and so on. So this was quite a challenging process, and at the end we couldn't find a single approach or single model that was doing good for both very low resource languages and also very high resource languages, because the quality or the precision recall metrics that you're actually aiming at are a little bit different. So what we did for low resource languages, we utilized a simple hand-tuned approach with curated data with curated data that we used word lists and so on, and that was actually working well for filtering low resource languages. And for high resource languages, we trained some semi-supervised models that were looking like, you can think of them like a BERT that has a language identification classifier. So those semi-supervised models, that they were actually doing quite good on high resource languages. So by doing so, we were able to, by basically making use of multiple models to crawl the entire web once again, we were able to get like monolingual data for quite a lot of languages that are like even beyond 400 on the plot that I've shown. So I'm gonna speed up here a little bit because this is just the end of the first section. The other sections are actually shorter, but just to summarize what we've seen in the first part, so massive multilinguality delivers huge gains for mid to low resource. There's still a problem in one-to-many direction, which exhibits a different transfer dynamic. So it's even massive multilinguality is not actually helping that much on one-to-many scenario. But we also showed we can easily build complete models. We showed a couple of ways to ingest or make use of monolingual data with self-supervised learning. And we also showed this multilinguality was mitigating several issues of unsupervised MT. All right, I'm going to go into the second part, which is the modeling of massively multilingual models. And in our models, so I didn't talk up until now, I did not talk about what model that we were using. I just mentioned briefly we were using transformers, but we were using a slightly tweaked transformer that's pretty much the same, but it's slightly bigger with a different normalization order and with a few other tweaks so that I mentioned here, but those are not actually major, so I'm just going to quickly skip this one. But another important thing for multilingual models or multitask models is about what you are sharing in terms of the parameters in the architecture. So here I just plotted 3 different paradigms, or to the evolution of the sharing paradigm in multilingual models. On the left, you're seeing only a fixed length representation was shared across all languages. In the middle, you're seeing some subcomponents are shared across all languages, and each language has its own component. And on the right, you're seeing the entire machinery being shared. So we're going to be using in our experiments the left-hand side, the rightmost approach, where we share everything, but we're going to be showing the deficiency of this model being monolithic, basically sharing everything. So the final solution is actually somewhere in between the second one and the third one. But since the amount of languages is huge, so it's not easy to handcraft or design this architecture. So we're going to be resorting conditional computation, or learning what to share and what not to share. So our recipe was basically simple. All these models that they were transformer big models, and they were sharing everything. As you share everything, the transfer, you're basically using the transfer, but also you're amplifying the interference that's happening across high resource languages. So they all fight for the same capacity. So the question is, if I'm in a monolithic architecture, how am I going to boost the quality of this left-hand side? So the question is actually a little bit trivial, or the answer is a little bit trivial. So we need greater model capacity. But how are we going to increase the model capacity? Should I make my model deep? Should I make it wide? and how is it going to affect the generalization or transfer dynamics in this model. Another thing is I can make the model densely scale, or I can also make my model sparsely scale using the techniques that I'm going to show soon. But just to give a landscape of scaling, so this is a chart in terms of number of synapses in both biological and artificial system. Just to put things into perspective, the original NMT was on the left-hand side. The transformer is here, has a little bit less synapses compared to a honeybee. So T5, Megatron, they're actually in this somewhere between honeybee and mouse brain. And the models that we'll be talking about, GPT-3 and M4, they're still far behind compared to the number of synapses in a mouse brain. But now we're in the scaling business, and we're scaling the models up and up. Here, what we're showing, if you remember this, like our old model that was in light blue, this is a transformer big model, and compared to bilingual baselines, we were seeing some regression on high resource. But as we scale them up and up, they were actually getting better across the board. But we did one experiment. We controlled the amount of the number of parameters, and we made the model either white, that is basically the orange curve here, and we also trained another model with the same number of parameters, but we just made it deep. So there's actually interesting phenomenon happening here. As we make our models deeper, they exhibit better transfer dynamics towards the low resource languages. So if generalization is about maximizing transfer, so we can indirectly say, yes, deeper models generalize better. There is some theory also in line with it, but there's also like counter examples. But this is more of an empirical finding that we have. But if you want to maximize transfer towards low resource languages without losing too much, it's better to make your models deep. And if you can actually go beyond, you can make them even like bigger or deeper. There we have like here, we just wanted to show as we scale, things get better and better. So here on the final model is basically a model that has 128 layer that's been trained using the tool that we call GPipe. But these were all dense scaling approaches. Dense scaling is, although I suggested training a very deep model, I didn't tell about how long was it taking to train that model, which was almost 5 weeks to train that 128 layer transformer on the available data that we had. But the other approach or other line of research to scale the models is basically sparsely scaling the model. There we're going to be using conditional computation, which means only part of the network is being activated for a particular example. So the examples are going to be routed through the network. So here I have actually a sketch. Here we have a dense model and 2 data points. We batch them, and this is basically the execution. They go layer after layer after layer with dense computation. But in a sparse model, the computation or the route that these examples follow are a little bit different. So here we have the common blocks that we already have, layer 1, layer 3, and the head. So these are basically a transform. You can replace them with any transformer layer that we have. These are common blocks, and we basically inject expert layers in between these common blocks. So these expert layers have experts and a router and a combiner. You can find different names for these, but they basically expert model that may be the same transformer feed-forward layer or any other layer. But at the end, how does the computation being executed in a sparsely activated model? So they follow the first layer, they go to the router, and the router decides, okay, these examples should go 2 experts, and it decides which expert that these 2 experts should go. These data points should go, and then being processed. After being processed, they're being combined by the combiner. That's these router and combiner, they're tiny neural networks. And that's all they do. They route and then combine the activations. And then it follows the same routing strategy on a different expert layer and so on. So this is pretty much the flow of a sparsely activated model. And what we did, what we used in terms of following the sketch, we use mixture of experts in order to scale the model size. If you notice this here, in order to increase the number of parameters, we can actually make this expert layer fat and fat. So we can actually add so many layers, so many experts. So that will inflate the number of parameters. And if you can train a smart routing strategy or routing neural routing network, so you will benefit both the transfer, and also you will sometimes have capacity that is not shared with all the other languages. So it's somewhere in between sharing everything and having some language specific components here, that as components being the experts we have. So here is the sketch of the actual implementation in a transformer model. We basically replace every other feed-forward layer with an MOE layer. An MOE layer also has these feed-forward layers, but say in one layer we don't have only one feed-forward layer. We have say 512 or 2,000 experts. So by doing so, we were able to go beyond 50 billion, 10 billion. 10 billion and 50 billion. Here we are showing two mixture of expert models, again compared against bilingual baselines. Apologies. And we're seeing as we scale more and more, we observe high resource languages are getting their capacity that they were needed. So we see the same transfer dynamics on the right-hand side. So low resource languages are improving, but high resource languages also getting their share of unshared capacity, so that they can make use of the data that's available. So that's that's not where we stopped. We developed another tool that is called G-Shard, and we kept scaling the models all the way up to 600 billion, where we hit the trainability issues. We were also able to put a trillion weight model on the chip or on the devices that we had, but we were not able to so far train or optimize or make that model converge with the given data. But here the take is quite similar. As you scale, you get more and more gains. So honestly, no surprise. So at the end of this phase, well, we had two insights. We showed the deep models were actually doing quite good the deep models were doing quite good on low resource transfer, but sparse models that they were actually quite good on securing some capacity for high resource languages. So the final solution is it seems to be best of the both worlds, basically making a mixture of expert model quite deep, which we don't have the results here yet. And on the right-hand side, we also are seeing another example, insight. No matter how much we scale, all the plots that I shown were always into English. So no matter how much we scale, we were not actually observing too much gain when we're translating out of English, basically when the target is multilingual. So these are still two open problems that we're actively working. Right, okay. Here, what is next? That what we're working more routing strategies that are informed by the gain on one particular language, or having secured more capacity for some experts, basically homogeneous experts, heterogeneous layers, or mixing both of them. And we're also actively working on meta-learning approaches to learn what to share and what not to share, and not relying only on the routing network to learn everything for us. So basically adding another loop on top to control the entire learning process. Since these two topics are actually, I was going to put papers, but they're under review, so I did not put them here. So in a couple of weeks, you'll see some papers in these two, but I'll be happy to talk if there is interest at the end. So since in the interest of time, I'll go faster, and I'll talk about the training regimes and optimization. So at the beginning, I talked about a green curve, blue curve, and I said, okay, let's just forget about the the blue curve. So that blue curve was that actually corresponds to a model that is being trained directly on the data distribution that is at hand. Basically, you do not touch the data distribution, and you randomly sample examples, and then you train your model using that data without changing anything. So that's what we were doing in the very first try, in the very first days of neural machine translation, multilingual machine translation. But we later noticed actually rebalancing is a good heuristic to use. But here we're going to see rebalancing or balancing is a quite challenging and difficult problem because we have hundreds of languages right now, and like simple heuristics like sampling, they're not really scalable. So they actually break beyond some point, or they end up being suboptimal. So there are also approaches to learn how to sample. And I think Graham and Cindy has a nice paper about this, which is doing something that a lot smarter than simple sampling heuristics are doing. The second approaches are the second bullet here, second line of research. So the first one is you can look at the data and you can try to change something in the data, and then you can form your batch and update your model with the information that you get from the data. But another line of research is you can also look at the model, internals of the model. Okay, what does my model think about this data? And is it already easy for this language to be learned so that I can actually discard these examples? Or if two languages are similar, can I actually manipulate the learning signal in a way to boost the quality or basically mitigate the fact that I don't have that much data for that language? So those are the techniques that either alter the learning rate or alter the gradients. And the third approach is basically the approaches that look at both at the data and also at the model internals. But I think the research is now being developed. We don't have any concrete papers or concrete research on this direction. And if you find this line of research interesting, and I think there is a lot of room for improvement on that direction. So the first one I mentioned in the previous slide was rebalancing the data with temperature. Here we see like simple rebalancing is actually boosting the quality quite a bit, but it's doing good up until, so it's expected to be suboptimal because at the end you're basically tweaking one hyperparameter, which is a temperature, and I think that is already covered in this course, so I'm going to skip that one. So the second one is basically looking at the internals of the model, but what you should be looking at inside of a neural machine translation model is quite tricky because these models are like black boxes. So what should we be reading from the model is a big question. And the thing that we were reading from the model, is it going to be reliable or not, is another question. And our first try was basically, so this is a little like equation story about that. I'll just summarize it. Our first try was coming up with an adaptive schedule that was weighting the tasks or weighting the gradients of the model by reading some things from the model itself. So what we were measuring was, okay, I showed you a batch and how much loss that you observed after the loss improvement that you observed after seeing that batch. And so we were solving this problem as a bi-level optimization. And here in the equation at the bottom left, so let's just look at the WI. That is basically the weight that I learn in an outer loop for the task I, and that I was using that learned weight to change something in the model. And in this case, we were changing the gradients for that task. What we noticed later on, the gradient of that task, or changing, amplifying that, or altering the gradient only, was not actually doing good because it was dominated by the learning rate that was hand curated. Here you're seeing on the right top. So this was actually a failed attempt. Then we said, okay, why don't we learn the learning rate itself? So if you basically, there are simple techniques that you can use to learn the learning rate. So if you take the derivative of your loss function with respect to the learning rate, and if you shift the loss function with one step, you can it gives you actually a closed form solution, which can be interpreted as if your current direction or update direction is agreeing with the previous update direction, then just increase the learning rate, otherwise decrease. And this is the same. You'll find this similar formulation or this dot product in quite a lot of other papers that are using bi-level optimization. Here we used it to learn the learning rate, and it was quite interesting to see. It was almost replicating the transformer learning rate schedule. But there were two problems in these approaches. The first one, our first attempt was not scaling, and the second one was quite brittle. So there comes the third one. So we wanted to find something that is both scalable and not brittle. And we started to study more rigorously by analyzing the gradients of different tasks. And I think the author, Siri, is here as well. So I'm going to be talking about the gradient vaccine that he proposed. And the paper started by investigating the gradients. Okay, let's look at the gradients of all these languages, and let's look at their similarities throughout the training. And surprisingly, what we found was the similarities were roughly reflecting the language proximity or language relatedness. So this was quite interesting because this was naturally happening when we were looking at the internals of the model. Another thing that we found quite interesting was as the gradients were getting more and more similar, they were also also positively affecting the model quality. Here on the left, you're seeing the gradient similarity between 7 languages on the many to English case, and here we know the similarities are quite high, and we also know the quality of translation is also quite high. But if you look at the English to X direction, there we observe the gradient similarity is actually low, and also the quality is also quite low. So given these two observations, first, it's the gradient similarity reflects language proximity, and similarity correlate positively with the model quality. We decided, okay, why don't we manipulate the direction and the magnitude of the gradient during the training process. So what we were doing was simply we were trying to align conflicting gradients or gradients that were not agreeing enough throughout the training process. So that we called gradient vaccine. So here, let's follow the sketch here. On the top left, you're seeing 2 gradients. The blue one is my main task that I'm confident in its direction, and the red one is the task that I'm not really confident in its direction. You can think of blue one is basically a high resource language gradient, and the red one being a low resource language. So here what you see is these 2 gradients are actually conflicting, or they have negative similarity. And throughout the training, if you observe such a case, we try to project it onto another. It's we were trying to make it align with the original gradient or the primary gradient, which is given in blue here. And we were trying to make them align throughout the course of the training. And so by doing so, we were always ensuring the gradients were the gradient similarity was always high between any 2 language pair. And we also replicate, there are a couple of actually similar approaches doing similar stuff. That the most common one is PCGRAD, that is doing this correction only when the gradients are conflicting. But we noticed actually, even when the gradients are positive, have positive similarity, it may still be harmful for the optimization. So we actually enhanced that approach And we came up with this technique that we assign a target similarity, and we always project the gradient of the conflicting gradient, or to an angle that is always aligning well or positively correlating with the target gradient. By doing so, here you're seeing the results on this massively multilingual model that has 25 language with different data sampling strategies. But gradient vaccine is given in green. That was actually always improving the quality both into English and out of English direction. All right, this is the end of the third section. So to summarize, sampling heuristic can become suboptimal at scale. And if you carefully choose what to look in the model, so they can be quite handy. And even simple gradient manipulation can go a long way, and also it scales. So the last part, so last two parts are quite verbal or verbose. So I'll be talking about the systems at the age of giant models and why we should be actually paying attention what's happening in the systems part. Because if you look at the components of an NMT system, so we have a training module, we have an inference module, and we have an evaluation module. So here the training is where we train our giant model. Inference is where we decode the model given run inference on a trained model, and evaluation is where we score some data. So in our model, in our setup, these three are happening simultaneously. So, and under the hood, this is pretty much what's happening. You're sitting at your home, you're connecting to a virtual machine on the other side of the country. So that is kicking up a trainer job that is in, like say, in Canada, and that is basically running two additional jobs, decoder, evaluator, that are in the different places and on the globe, reading data from a data center that's in Europe, and then again communicating with the decoder jobs that are all around the world, and then at the end collecting all this data and then reporting you back the result. So how is this being orchestrated is quite crucial. And on the software side, we are using a tool called Lingual. This is open sourced already. If you're curious, you can just take a look. But at the age of scaling, there is actually one more detail. That is, as we scale models, the quality is improving. This is a plot from GPipe, and this is another plot from G-Chart, just to support the argument as we scale, things are improving. And these models are actually using multiple trainer jobs. So they're actually, even the model is being distributed. And here you're seeing a TP version 3 pod, but these models, since they're giant, they're actually being trained on multiple data centers that are also distributed across the globe. So this orchestration, although we think it's seamless, once you want to scale your models dramatically, you end up not being able to, you end up with no tools that are able to do it. So we had to actually invest quite a lot on the tools as well. That's where we end up with GPipe, which was using pipeline parallelism to train very deep models and then mitigate the communication bottlenecks. And also we developed G-Shard, which was doing automatic sharding, basically distributing experts into different chips and making this communication quite efficient and easy. So we have just one lesson learned. The tools and system in order to orchestrate these giant machinery is essential. If we didn't have GPipe or G-Shard, we wouldn't be here today in terms of the entire project. So at last, the cross-lingual downstream transfer. You might be asking, okay, you trained all those giant models on hundreds of languages, but so what's in it for me if I'm not working on machine translation or I'm working on a different task? So there we followed a very simple approach. We trained these networks and then dropped the decoder. If you think about a transformer encoder decoder architecture, its encoder is basically a BERT, but trained using a supervised objective. But what we did was we picked up a transformer, we picked up an M4 model, which was actually an M3 because it wasn't massive, but it was only massively multilingual. We dropped its decoder, and then we treated its encoder as if it was BERT. And we applied it on, we basically tested it on several downstream downstream tasks. And it was, we noticed it was actually quite good on a couple of tasks, at least 4 out of 5 tasks. It was quite competitive, and this was coming as a byproduct of training a machine translation model. And it was actually doing particularly good for low resource languages, which we noticed here in this plot. We're basically showing its performance on XNLI and part of speech tagging, and compared to BERT, multilingual BERT, it was doing better on low resource languages. We attained this quality gain to the fact that our model was actually good in terms of, our model has an implicit separation of many to English and English to many. So this was actually playing a role on high resource and low resource languages. If you're interested in, please take a look at the paper in the previous slide. I'm gonna wrap up quickly. We also tested the very same encoder on Extreme Benchmark. It was again quite competitive compared to the number of parameters that it had. And we, I just wanted to say the models that we tested, they were actually all M3 models. And unfortunately, we didn't invest much on evaluating M4 models, which are at scale on all these downstream tasks. So it will be quite interesting to see how they perform on Extreme or in other benchmarks. So to summarize everything, and I think I'm being a little bit, I'm going a bit over time. So what we did cover, we covered 5 different aspects of massively multilingual and massive models. But what we did not cover, they're also quite interesting. We didn't cover what does generalization mean in machine translation, or given that we're having an evaluation crisis these days in machine translation. Now we have translationese effects, or distillation effect, or back translation effect. So we actually haven't talked anything about that. We also haven't talked anything about the noise in the data. What happens, like I showed you the data distribution, but what happens that was actually the raw data that was available. But like, can I actually squeeze out more quality if I clean the data or augment data? So we actually did not talk about that. We also didn't talk about inference dynamics, how we are serving these models, or how we're what is the serving latency if I want to like put the system in production, or what are the distillation routes if I want to distill a giant model into a smaller one, and what is the gap between that like billion scale model versus a transform big. That we also didn't talk. And all the experiments here, that we're relying on sentence level data, but since we are using giant models, we could also use some contextual data, or more like beyond sentence level data. Here we didn't talk about it. It's, I think, a very exciting direction. And at last, we also didn't talk about the input and output granularity in terms of subwords, characters, bytes. There's a lot of research needs to be done and already been done, and it's also an interesting direction. So I put some challenges and open problems if we have time for discussion, but I see I'm already 3 minutes over time. But I'll stop here. Thanks everyone for listening. And again, thanks Graham for the invitation.
Yeah, thanks a lot, Orhan. This was a very extensive talk about lots of different directions. So I think, you know, probably many people found something interesting to them here. I think, you know, if people want to drop off, that's fine, but the floor is open for questions. I'm sure we can do before we finish up.
I have a question. Firstly, thanks for the really amazing talk. And so my question is that in terms of practical importance for Google, how important is it for having one model that can serve translations for many languages? Like, is that something that the engineering teams have asked for, or is that done more as a research question?
It's both. When you say Google, the first thing that comes to mind is, I think, the scale. And over the last couple of years, there is one significant trend. That's a trend that is quite striking. That is, the only predictable gain in terms of quality is attained by scaling the models. So we now have models that are scalable, that we know how to scale, which was not the case when we were using LSTMs. They were quite hard to scale and also hard to train. But now we have transformers, and I think that changed the landscape quite a bit. They scale quite nicely, and if you also follow up the papers from, for example, OpenAI in terms of the scaling laws, the neural network scaling is almost predictable, at least empirically. There's also a couple of other papers from Baidu and other research institute, other companies and so on. The only safe bet seems to be scaling up models. So that's why as we scale models up, we're seeing more and more quality gains, and we're still searching for the point where it's going to saturate. Because this, as you scale, you hit another wall, which is usually optimization. As you mitigate the problems, or as you fix the problems in optimization, you end up being bottlenecks in the information flow, either in the forward pass or in the backward pass. So that's why I think the engineering and research is going they're going together. So I think this is going to be the trend for a long time. I don't know if it answers your question, but this is my personal view. I don't know, high-level politics at Google. Yeah.
Okay, thank you.
I have a question. So you're trying to improve the high-resource languages, and the high-resource languages are pretty good at the moment. And the low-resource is great that you're doing that too. Do you think you're getting to a limitation of BLUE, or do you just think that optimizing on BLUE is still going to improve everything? Or should you be trying to do something else? Because, as you hint, some of your data might suck and you might be better than some of your data. So maybe another evaluation metric might be better?
Certainly, you're so right. Yes, that was the first thing that I mentioned, that the things that we did not cover, but so essential. I totally agree. And in our evaluations, for critical high resource languages, for a subset, selected subset of them, we usually go to human evaluations. So for some certain cases, when the data is not polluted by translationese or back translation, or if you don't use distillation, we found the BLUE score is correlating well with the human evaluations. So we use BLUE score as a proxy only if needed, but honestly, we're mostly looking at the perplexity, how well the model is fitting on the data that is at hand. And if you can ensure the amount of data is almost infinite, so that has different properties if you have a good fit on your training set. So there will only be a delta gap between your training perplexity and your test perplexity. So that's also another proxy to measure the generalization from the machine learning sense. Okay. But yeah, I totally agree. Yeah, BLUE scores are not really reliable. There are so many confounding factors contributing.
Yeah, so I had a question about the routing kind of network that you were talking about. I believe you were calling it transformer MOE. So I believe you're also learning the routing, right, to the expert?
That is correct, yes. Routing network is a tiny network. It's basically like a few layers neural net, like few-toward neural net, that is learning to route which example, given an example, which expert that it should go.
Gotcha. And when we say expert, we're talking about in a generic bagging kind of a scenario, like calling an expert a full network kind of an expert, or is it?
That is correct. Yes, that's correct. Yes.
And from the
Yeah.
results that you showed, if I get it correctly, for a similarly parameterized, like a normal transformer model, the transformer MOE was kind of performing worse than a similarly parameterized transformer model. Am I right with that?
Similarly parameters, you mean which has the
S-
same number of parameters?
yeah, same number of parameters. That's right.
That depends on which languages that you're looking at. If you're looking at high resource language, it's actually on par because it has the capability to spare some capacity to high resource.
Mhm.
But on low resource, it was actually regressing. Yeah.
Got it. Because from what I saw, if I remember the figure correctly, I thought like the normal transformer model had around 6 billion parameters, whereas like the MOE had around 50 billion, if I'm like not wrong.
Oh, okay. Just a
Yeah.
second. Let me go to the slide. Which one you're talking here? This one? Is that
The next one maybe.
here?
We had like the comparison, the side by side left and right comparison. This
No.
one, yeah. This one.
This
This one.
one?
Yeah.
Ah,
So
okay.
if I look to the one on the left,
Mhm. So
So-
here, this is a 6 billion. So the here dark blue is a 6 billion dense model.
Mhm.
And the green one is a 50 billion parameter sparse model. So they
Gotcha.
have different. So if you look at the dense model, it's actually quite good on low resource transfer compared to MOE model.
Yeah.
But MOE model is actually doing quite good on the high resource language. So that's what I meant by
Oh.
it can spare some capacity.
Got it. Got it. Completely got it. Thank you.
Great. If we have one more question, maybe we could take one. If not, we can wrap up. Okay. If not, I might have some follow-up questions, but I'll ask via email or something to not keep everybody around. So yeah, thanks a bunch again to Orhan for agreeing to give this talk. And we'll try to make the video and the slides available so you can take a look and go back and see all the references if you missed any of the ones that sounded interesting. So yeah, thanks again. And see everyone on Thursday, and see you, Orhan, sometime soon when I see you.
Thanks everyone. Bye.
Bye. Good night.